Okay, this is a new chapter, chapter 4. It's all about heat and thermodynamics. We will see here laws of thermodynamics and the concept of heat. So, here we have thermodynamics is a science of relationship between heat, work, temperature, energy. So, whenever we deal thermodynamics, we have to consider thermodynamic variables like pressure is one of the thermodynamic variable. Volume also one of the thermodynamic variable. So whenever we calculate work, we will take those thermodynamic variables under consideration. Okay, so a broad term, thermodynamics deals with the transfer of energy from one system to another system or from one form to another form. So when a system exchange energy with each other, we have to consider some important pointers like thermodynamic process, state variables, equation of states, and so on. Okay, so having this in mind, the three thermodynamic systems are the following. The first one is closed system, second one open system, the third one isolated system. So there is a difference between this closed system, open system, and isolated system. So in case of isolated system, the system do not exchange either heat or for energy or particles with the other system or with the surrounding. So such type of system is called isolated system. And the other one is open system. In case of open system, the system exchange particle as well as energy with the other system or the surrounding, and such type of thermodynamic system is called open system. When you see a closed system, it is different from the two, where here there is exchange of energy but there is no exchange of particle. It takes it shares with open system regarding the exchange of energy, but it shares no exchange of particles from the isolated system. Okay, so for more elaboration, let's take these three example. This one is taken to be as an example of an open system. Here we have there is heat transfer and mass transfer. So the particles inside this one can join the surrounding, and there is also exchange of energy between the surrounding and the system. And sometimes it's possible to consider this one as a closed system. A closed system, the heat can transfer. This one will allow heat to transfer to the environment, but there is no particle, there is no way to the particle passes this cover. So this can be considered as a closed system. The other one, this one is isolated system, so thermoflask. So this isolated system, there is no heat transfer, no mass transfer. So the system is considered to be an isolated system. So in general, the three thermodynamic systems are closed system, open system, and isolated system. Now let's proceed to the next topic. So thermodynamic system. There are important pointers here. The surrounding, whenever you say in thermodynamic system, the surrounding is the environment that is around a system and in thermal contact with it. So the other one is system itself. System is defined as part of the universe which is chosen for thermodynamic study. The other is boundary, the actual or imaginary line which separates the system and surrounding is known as boundary. By the way, there is a fixed boundary and there is a movable boundary. Sometimes there is also imaginary boundary. For doing some calculation, we imagine some boundary or we draw a boundary, and that boundary is considered to be imaginary boundary in a system. Okay, so this is a best example regarding these three important constituents. First one is this one is surrounding, this one is a system, there is a boundary. So this one is a system, this is a system which has a certain solution, and this is a boundary. The glass is considered to be boundary, and the other thing around this system is considered to be surrounding. Okay, so the next slide, general thermodynamics. General thermodynamic system is defined by its temperature, volume, pressure, and chemical composition. They are called thermodynamics variable, by the way. So a system is in equilibrium when each of these variables has the same value at the same point. So each state described by the equation of state. In those equation of state, these thermodynamics variables are present. So with this one, we build the equation of state, and whenever we say equilibrium, so we have to say that this variable thermodynamics variable has the same value at all points in the thermodynamic path or in equation of state. So whenever say equilibrium, we have to consider three things. One is chemical equilibrium, the other is mechanical equilibrium, and the other is thermal equilibrium. So in case of thermal equilibrium, we consider the two systems, for example, they have the same temperature. In case of chemical equilibrium, so we have to consider the chemical potential of the two systems should be equal. Mechanical equilibrium, we need to consider pressure. Okay, so now let's take this one. There is a boundary and there is a surrounding. So this is system A and system B. So this first system has this thermodynamic variable like pressure, temperature, and volume. This one also has pressure, temperature, and volume. So whenever we compare the two systems, we have to see this thermodynamics variable. Based on this one, it's possible to talk about the equilibrium condition of the two systems. Okay. Next to this one, we have to see the concept of temperature, Zero's law of thermodynamics. So first we start from heat. Heat is defined as a flow of energy from one object to another. This flow energy is caused by a difference in temperature. So the other thing that two objects are in thermal equilibrium if they are in close contact that allows either to gain or energy from one to the other. For example, if we consider two closed systems, so when they are in contact with each other, after some time they will have the same temperature. So in this case, it is possible to say that the two systems are in thermal equilibrium. After a certain time interval, the temperature will be equal. The temperature of the first system and the temperature of the second system, in this case, equilibrium. So after they acquire thermal equilibrium, so there is no net energy exchange between the two systems. Okay, so if two objects remain in contact for a long time, they typically come to equilibrium. Consider this one, object 1 and object 2. For example, this may be at higher temperature. As you can see, temperature 1, this is higher, this is at lower temperature. So in this case, the two systems are in thermal contact. So after some time or after a long time, so the two systems will have the same temperature reading. And this one lose energy and this one will gain energy. Then finally they will have the same temperature. Okay. So the other one is Zero's law of thermodynamics. Whenever we talk the laws of thermodynamics, like Zero's law, first law, second law, and third law, here we have to consider important Zero's law of thermodynamics. So whenever we talk about Zero's law of thermodynamics, we have to see system A, system B, and system C. So one of the system can be considered as a thermometer. So if we take thermometer system A and take that thermometer and insert to one of the system, let's say system B, if the thermometer reads 50 or 50 degrees Celsius, and then take that thermometer to the second system, system C, then if that thermometer reads a temperature of again 50 degrees Celsius, in this case we can say that system A and system B are in thermal equilibrium, and system A and system C are in thermal equilibrium. Therefore, it is possible to say that B and C are in thermal equilibrium. Okay, so for the if object A, which is system A, is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. That statement of transitivity is called Zero's law of thermodynamics. Look, this is B and this one is C. Now take A as a thermometer and insert here, and it reaches the same temperature for system A and system B. In this case, system A is in thermal equilibrium with system B, and system A is in thermal equilibrium with system C. Therefore, B and C are in thermal equilibrium. So this is what we have regarding Zero's law of thermodynamics. Okay, so after this we need to see temperature scale. Thermometers measure temperature according to the well-defined scale measurement. So it can be measured degree Celsius, degree Fahrenheit, or in Kelvin. So this can be for basis of thermometer. One is volume increases with temperature for most substances. One is alcohol thermometer. The other is original mercury. You know, mercury thermometer. So the liquid that we use inside of the thermometer is mercury. Sometimes it's possible to use alcohol. Here is a picture for this one. This is an example that it's a mercury thermometer. So when this mercury gets heat or energy, so there is an expansion of this fluid. Then with that, it's possible to reach the change in temperature. Okay, so the other property used to measure temperature are electrical resistance, color, the emission of infrared radiation. All these can help us to measure the change in temperature. This is an example with the change in electrical resistance, so it's possible to measure the temperature. Okay, so having this in mind, now thermometers measure temperature according to well-defined scale measurement. The three most common temperature scales are degree Celsius, Fahrenheit, the second one degree Celsius, the third one is it's in Kelvin form. So this can be shown by using this diagram. So as you know that the boiling point of water is 100 degree Celsius. When we interpret in terms of degree Fahrenheit, it is 212 degree Fahrenheit. In terms of Kelvin, 373. In terms of Kelvin, it is 373 degree Kelvin. And you know how to convert one with the other. So the other one is freezing point of water. The freezing point of water is 0 degree Celsius. And in terms of degree Fahrenheit, this is 32. In terms of degree Kelvin, it is 273. And the freezing point of dry ice, carbon dioxide, is minus 109 degree Fahrenheit. And in terms of degree Celsius, it is minus 78 degree Celsius. In terms of Kelvin, 195 degree Kelvin. So boiling point of nitrogen, minus 321 degree Fahrenheit, minus 196, or Kelvin 77. So absolute zero is in Kelvin it is 0, absolute 0, it's 0, but degree Celsius is 273, degree Fahrenheit is minus 460.